In this video, I will show you how to graph inverses. So in this particular example here, on number 2, we're going to sketch the inverse of f of x and the line of reflection y equals x. So when we're done, we'll see that this parabola, its inverse, will be as if it was reflected across this line here, y equals x. I've already picked 5 values that were easily recognizable on part A here. So these are the coordinate points I found. Now, if you recall from an earlier lesson about inverses just take what was an input-output for a function and then just switch them. So the output becomes the input and the input becomes the output. So in other words, 10, 4, 2, 4, 10. All of these are now the input for the inverse. Okay, so all of these are the input for the inverse. And then the output values are negative 9, negative 7, negative 5, negative 3, and negative 1. So just switch the x and y as the real quick shortcut to graph an inverse given a function. So we'll plot the points. We've got 10, negative 9, 4, negative 7, 2, negative 5, 4, negative 3, and 10, negative 1. And then draw a curve through these 5 points. And we'll put arrows at the ends to indicate that it still goes on forever. So this inverse right here should look like kind of like the mirror image as if we reflected the parabola across the line of reflection to get the inverse. Now I intentionally made a mistake when I wrote my table here. You'll notice that I said x and then I wrote inverse function. But you should be like, hey, wait a minute, that's not a function. Definition of function says for each input you have one output. Well, here we have a lot of inputs. So like for example 6, when x is 6, it has 2 different outputs. When x is 10, we had both negative 9 and negative 1 as the output. So this is not a function. So I can't write that notation. I'm just going to write inverse by the graph. So I suppose I can make this table just x and y. Okay, but I certainly can't call that an inverse function. So I do want you to note that every function has an inverse, but not every inverse is a function. And this is a prime example of a quadratic and how its inverse is not a function. Okay, one more example here. I've got the table already started for us. So to quickly graph the inverse, just take every input, negative 6, 3, 1, and 9. Every output of fx, becomes the input for the inverse. And then all of these values here, the negative 11, negative 8, 3, and 6, are now the outputs. Now I'm going to be a little apprehensive here. I'm going to put y right here. Not quite sure this is going to end up being a function, but just in case, I'm not going to label that inverse function notation. So we have the point negative 6, negative 11, followed by 3, negative 8, I'll go ahead and start sketching as we go along here. So I can see that these two points were connected, kind of corresponding to the other one over here. And then we have the point followed by 1, 3. Okay, so 1, 3. And then the point 9, 6. Okay, so 9, 6. Okay, and then looking at that right now, we could tell that it is not a function. For example, when x is 2, it has 3 different y values that are possible. So it's a good thing we didn't label inverse function. But I can label the graph. I'll just write the word inverse because it is an inverse by definition of what we did. Okay, I'm going to go ahead and draw the line of reflection at y equals x. So to recap, how do we graph an inverse? you take the x and y values of a function and you just switch them. Y becomes x and x becomes y. Graph it, and then there's symmetry in a way that if you take the f of x and you reflect it across the line y equals x, you get the inverse function. I do want you guys to note, I was a little sloppy on this, but wherever a function and its inverse intersect, that is also the place where the line of reflection also intersects. Think about yourself when you look at the mirror in the morning when you're getting up. If you reach out your hand and you go touch the mirror, well, so is your reflection. So you're both meeting at the line of reflection in the mirror. The further you're away from the mirror, so is your reflection. So you can kind of look at it as, you know, here you're standing at the mirror and your reflection is just as far away as the mirror, you know, from the mirror as you're standing. But then if you reach out your hand to touch the mirror, your reflection is doing the same thing. And so all three curves, the function, its inverse, and the line of reflection, will all intersect at the same point.